Physics has a rulebook. One theory predicts the behaviour of every particle inside every atom in your body, with an accuracy so precise it would be like measuring the distance from New York to Los Angeles and being off by less than the width of a human hair. Scientists call it the Standard Model, and it works perfectly. Every single test, for 50 years. So why do the people who built it say it's broken? Because it misses 95% of the universe. It has no answer for gravity. It cannot explain why you exist. And tucked inside its equations are 19 numbers that nobody on Earth can explain. We are going to go inside the smallest thing ever discovered, meet the particles that build reality, find the invisible field that gives everything its mass, stare into the dark matter that surrounds every galaxy, and stand at the edge of what physics simply cannot answer yet. If you enjoy the journey, hit subscribe and leave a like. More of this is coming. Prepare yourself. We begin.
Picture the smallest thing you can imagine, a grain of sand. Now go smaller, much smaller. Keep going until you are 1,000,000 times smaller than that grain of sand. You are now inside an atom, and inside that atom, something extraordinary is happening. Particles are flying, forces are pushing, invisible fields are pulling, and everything is moving according to a set of rules so precise, so complete, that physicists spent 50 years writing them down. That set of rules has a name: the Standard Model. It sounds boring. It is anything but. The Standard Model is the closest thing humanity has ever built to a true instruction manual for reality. It tells you what matter is made of at the deepest level we can reach. It tells you what forces act between those pieces of matter. It tells you how a particle gets its mass, how light moves, how the sun burns, and why the chair you are sitting on does not collapse through the floor. All of that comes from one framework. Here is what makes it jaw-dropping. The Standard Model does not just describe what we have already seen. It predicts things before we find them. In 1964, physicists used it to say that a specific particle must exist, a particle nobody had ever detected. It took almost 50 years of searching, machines the size of cities, and billions of dollars to find it. But when scientists finally looked in the right place, in 2012, there it was, exactly where the math said it would be. That is not a lucky guess. That is the theory working. Now think about what that means. The equations physicists wrote down in the 1970s, equations full of symbols and Greek letters, contained inside them a truth about nature that no human could see for another 4 decades. The math knew before the machines could prove it. And the precision goes even further. One of the Standard Model's predictions, a property of the electron called its magnetic moment, has been tested in labs. The match between the prediction and the measurement is accurate to 1 part in a billion. Imagine predicting the exact weight of a blue whale and being off by less than a single grain of rice. That is the level of accuracy we are talking about. So why would anyone call this theory broken? Here is where it gets strange. The Standard Model describes everything physicists can directly touch, measure, or detect in a particle accelerator. But the universe contains far more than that. Everything you can see in the night sky, every star, every planet, every galaxy, adds up to roughly 5% of what the universe actually contains. The other 95% is something else entirely. Something the Standard Model has no answer for. Then there is gravity. You feel it every second of your life. It is the most obvious force in the universe. And the Standard Model completely leaves it out. And buried in the heart of the theory are 19 numbers, constants, that the model needs to make its predictions work. Things like the mass of the electron, the strength of certain forces. The model uses those numbers perfectly, but it cannot tell you why they are what they are. They have to be measured from nature and plugged in by hand, like cheat codes baked into the universe. A theory that predicts the electron's behavior to 1 part in a billion. A theory that misses 95% of everything. Both of those things are true at the same time. And the deeper you go, the stranger it gets. Everything around you is made of something. The desk, the floor, the air, your own body. Go small enough and you hit atoms. Go smaller than atoms and you hit the nucleus. Go smaller than the nucleus and you reach the level where the Standard Model lives, the level of elementary particles. Elementary means it cannot be cut smaller. No knife, no laser, no machine in existence can crack these particles open. They are the bottom of the ladder, the last stop before nothing. The Standard Model says matter is built from 12 of them. 12 fundamental particles. That is it. Every object you have ever touched, every living thing, every star in the sky comes from combinations of these 12. They split into 2 families, 6 quarks and 6 leptons. Start with quarks. You will never see a quark alone. They refuse to travel solo. Instead, they always bind together in groups, held by one of the most powerful forces in nature. 3 quarks together form a proton or a neutron. Those protons and neutrons pack into a nucleus. That nucleus plus electrons becomes an atom, and atoms build everything else. The 6 quarks have names: up, down, charm, strange, top, and bottom. Those names do not mean anything physical. They are just labels physicists gave them. What matters is the pattern. Quarks come in 3 pairs, arranged by mass. The lightest pair, the up and down quarks, are the ones that build the protons and neutrons inside you right now. The other 4 quarks are heavier, unstable, and only appear in extreme conditions, like the inside of a particle accelerator, or the first moments after the Big Bang. Now the leptons, 6 of them too. The most famous is the electron, the particle that orbits the nucleus of every atom and makes chemistry possible. Without electrons, no atoms would bond, no molecules would form, no life. The electron has 2 heavier cousins, called the muon and the tau. Both behave like electrons but weigh much more and fall apart almost instantly. Then there are 3 particles called neutrinos, 1 for each of the charged leptons. Neutrinos have nearly no mass, they carry no electric charge, and they barely interact with anything. Right now, billions of neutrinos produced by the sun are passing through your body every single second. You cannot feel them. Your body is essentially invisible to them. So that is the lineup. 12 matter particles, 6 quarks and 6 leptons, arranged in 3 generations that mirror each other by mass. Here is the twist that took physicists years to accept. Only the first generation matters for normal life. Up quarks, down quarks, electrons and electron neutrinos. That is all you need to build the entire visible universe. The second and third generations are like backup copies that are heavier and less stable. They show up briefly in violent environments and then decay back down into first-generation particles. Why does nature make 3 generations instead of 1? The Standard Model does not say, it just observes that there are 3. That question sits unanswered, and this is only the matter half of the story. Something else controls how these 12 particles talk to each other, something that carries force from one particle to another across empty space. That part of the story is even stranger. Stop for a second and think about your hand. It feels solid, it feels real. Press your fingers together and they resist. That resistance feels like proof that matter is dense, packed, full. It is an illusion. If you took a single hydrogen atom and blew it up to the size of a football stadium, the nucleus would be about the size of a marble sitting at the center of the field. The electron would be somewhere in the outer seats, buzzing around. Everything in between is empty space. All that emptiness, inside what feels perfectly solid, now goes smaller, down to the nucleus, down to the proton. Inside every proton are 3 quarks. And here is where it gets strange in a different way. The quarks themselves are almost impossibly small, but they are not just sitting there quietly. They are in constant violent motion, bound together by a force so strong that separating them takes more energy than it does to create entirely new particles. That force has a name. Physicists call it the strong force. The particles that carry it are called gluons, and the thing gluons do is remarkable. Unlike most forces which get weaker as distance increases, the strong force does the opposite. Pull two quarks apart, and the force between them gets stronger. It is like stretching a rubber band. The further apart they go, the harder the band pulls them back. Pull hard enough, and something extraordinary happens. The energy you put into pulling them apart becomes so large that it spontaneously creates a new pair of quarks right there in the gap. You tried to isolate one quark. You ended up with more of them. This is why you will never find a single quark alone in nature. Every time physicists try to isolate one, nature responds by producing more quarks to fill the gap. Quarks are permanently confined inside larger particles. Physicists call this confinement, and it is one of the most fascinating features of the Standard Model. Now here is the part that connects back to you. Every proton and neutron in your body is made of 3 quarks. An up quark carries a specific electric charge. A down quark carries a different one. 2 ups and 1 down make a proton. 2 downs and 1 up make a neutron. Those are the only 2 combinations that form stable particles you find in ordinary matter. Your entire body, every atom in it, is held together by the force between quarks and the gluons zipping between them. The solidity you feel when you press your hand against a table is not the quarks themselves. It is the energy of the strong force between them, the same force so powerful that nothing in the observable universe has ever broken a quark free. And that energy adds up. Most of the mass of a proton does not actually come from the quarks themselves. It comes from the energy of the gluons and the motion happening inside the proton. Energy and mass are related, as Einstein showed. So when you step on a scale, most of what you are measuring is the energy of a force you have never seen and cannot directly feel. You are mostly empty space animated by one of the most intense forces in nature. But there is another force inside the atom, one that does something the strong force cannot, one that can actually change what a particle is. Imagine 2 ice skaters on a frozen lake. They face each other and one throws a heavy ball to the other. When the ball leaves the first skater's hands, they get pushed backward. When the second skater catches it, they get pushed backward too. No direct contact, just the exchange of something between them, and both skaters move apart. That is how forces work between particles, except instead of a ball, they exchange a special type of particle called a boson, a force carrier. The Standard Model contains 4 known forces in nature, but it only describes 3 of them: electromagnetism, the weak force, the strong force. Each one is carried by a different boson. Each one behaves differently, and each one is responsible for a completely different piece of how the universe works. Electromagnetism is the most familiar. The particle that carries it is the photon, the particle of light. Every time 2 charged particles interact, they exchange photons. The electrons in your body repel the electrons in the table below you. That repulsion is electromagnetic. That is why solid things feel solid, not because matter is packed tightly, but because the electrons on the surface of objects push each other away through a constant storm of photon exchanges. The strong force is carried by gluons, 8 types of gluons, all massless, all moving at the speed of light, binding quarks together inside protons and neutrons. The strong force is, by some measures, 100 times more powerful than electromagnetism, but it only works at incredibly short distances, much smaller than a proton itself. Then there is the weak force. This one is different in a critical way. The weak force is not just a push or a pull. It can change the identity of a particle. It is carried by 3 heavy bosons, the W+, the W-, and the Z. And when a W boson is exchanged, it can turn a neutron into a proton, or vice versa. That transformation releases an electron and a neutrino. That process, called beta decay, is not some exotic lab curiosity. It is happening inside the Sun, right now. The Sun converts hydrogen into helium through a chain of reactions that depends on the weak force changing protons into neutrons. Without the weak force, the Sun does not shine. Without the Sun, there is no life on Earth. So 3 forces, 3 types of carriers, each doing something completely different. One glues quarks into protons. One pushes and pulls charged particles. One converts particles into different types and powers the stars. The elegant part is that the Standard Model treats all 3 using the same mathematical structure. Different forces, same language. That unification took decades to achieve and is one of the genuine intellectual triumphs of the 20th century. But there is a 4th force that stands completely outside this picture. The one force every human has felt every second of their life. The one force that shapes galaxies, controls orbits, and pulled the matter of the early universe together to form everything we can see. It is not in the Standard Model at all, and that absence is the first crack in what otherwise looks like a perfect theory. Deep inside the nucleus of every atom you have ever touched, a war is being fought. Protons carry positive electric charge. Put more than one in the same tiny space, and they push against each other with enormous force, like charges repel. That is electromagnetism doing its job. So how does a nucleus stay together? How does any nucleus with more than one proton avoid blowing itself apart? The answer is the strong force, and it is exactly what it sounds like. The strong force is the most powerful force in nature at short range. It overwhelms the electromagnetic repulsion between protons and holds the nucleus together. The margin is not close. The strong force is roughly 100 times stronger than electromagnetism at the distances inside a nucleus. But it has a catch. It only works at incredibly short distances. Distances smaller than a proton itself. The moment 2 particles drift more than a few femtometers apart, which is a unit so small that it takes 1 quadrillion of them to equal a single meter, the strong force drops to almost nothing. It vanishes as quickly as it appears. That is why nuclei cannot grow forever. Make a nucleus too large, and the protons on opposite sides are too far apart for the strong force to reach across. The electromagnetic repulsion starts winning. That is the physics behind radioactive decay. Very large nuclei are unstable because the strong force cannot hold all those protons together across such large distances. Eventually, the nucleus breaks apart. The particles that carry the strong force are gluons. Unlike photons, gluons have a strange property. They carry the charge of the force they transmit. Photons carry no electric charge. Gluons carry what physicists call color charge, which has nothing to do with actual colors. It is just a label for 3 types of strong force charge: red, green, and blue. Because gluons carry this charge, they interact with each other. They do not just travel between quarks. They bind to each other, creating tubes of force between quarks called flux tubes. These tubes are what make the strong force behave so unusually. Instead of spreading out in all directions like gravity or electromagnetism, the force is concentrated into a narrow channel between the quarks. It stays intense no matter how far apart the quarks move. Stretch the flux tube far enough and it snaps, but snapping releases energy, and that energy creates new quarks. Nature fills the gap every time. This confinement of quarks inside protons and neutrons is one of the most tested predictions of the Standard Model. No quark has ever been observed alone. Every experiment that has ever tried to isolate one has failed, and failed in exactly the way the theory predicts. Here is the consequence that touches your life directly. About 99% of the mass of your body comes from protons and neutrons, and most of the mass of each proton and neutron comes from the energy of the gluons and the motion they create inside those particles. You are, in a very literal sense, mostly made of the strong force. The quiet, invisible war inside every nucleus is the reason you have weight. the reason planets have gravity, the reason the universe has structure at all. And yet the force that does all of this still has a mystery at its center, a deep mathematical puzzle called the strong force problem that no physicist has fully solved. That puzzle has its own $1 million prize waiting for the person who cracks it. But first, the weak force has something to say. And what it says is far stranger than anything the strong force does. Most forces just move things around. Gravity pulls. Electromagnetism pushes and pulls. The strong force holds particles together. But the weak force does something none of the others can do. It changes what a particle actually is. Think about that for a moment. A force that walks up to a particle and transforms it into a completely different particle. That is not just pushing, that is rewriting identity at the most fundamental level. The weak force acts through three carrier particles: the W+ boson, the W- boson, and the Z boson. These are heavy particles, much heavier than protons. Their mass is why the weak force works at such tiny distances. The heavier the carrier, the shorter the range of the force. The weak force operates at distances far smaller than a proton's width. Here is the transformation that matters most for everything alive. Inside the sun, protons collide constantly at extreme temperatures and pressures. Occasionally, during one of those collisions, the weak force steps in. A W boson is exchanged. One of the protons loses a positive charge and transforms into a neutron. At the same moment, a positron, which is a positively charged mirror of an electron, shoots out along with a neutrino. That transformed neutron and proton bind together. Through more steps involving more weak force interactions, 4 hydrogen nuclei eventually fuse into one helium nucleus. The mass of that helium nucleus is slightly less than the 4 hydrogen nuclei it came from. That missing mass becomes energy. Enormous amounts of energy. Energy that has been streaming from the sun for 4.5 billion years, and that sustains virtually all life on Earth. The weak force makes the sun shine. Every ray of sunlight that has ever touched your skin passed through a chain of events that started with the weak force changing a particle's identity. Now here is the part that surprised physicists. The weak force breaks a rule that every other force follows. It treats left-handed and right-handed particles differently. This is called parity violation, and when it was discovered in 1956, it genuinely shocked the physics community. Scientists had assumed that nature would look the same in a mirror. Swap left and right, and the laws of physics should be identical. The weak force said no. That asymmetry turned out to be a clue about something much bigger. The difference between how the weak force treats matter versus antimatter is subtle, but that subtle difference may be connected to one of the deepest unsolved problems in all of science: why matter exists at all instead of antimatter. The weak force gives us sunlight. It bends the rules of symmetry, and buried inside it may be the reason you are alive. But the weak force and electromagnetism are not actually separate. At high enough energies, they merge into a single force. That unification, discovered in the 1960s and 70s, was a landmark achievement. It showed that two apparently different forces are actually two sides of the same thing at extreme conditions. And that hint of unification points toward a question that has driven physics ever since. If two forces can merge into one, could all the forces be unified at some deeper level? The answer might require a particle that was predicted decades before anyone found it. You are surrounded by them. Right now, billions of them hitting your skin, bouncing off every surface in the room, streaming through windows and walls, and the air itself. Most of them you cannot see. The ones you can see make up a sliver of the full picture. Photons, the particles of light. And the word light undersells it completely. Visible light is just one narrow band of what photons can be. Radio waves are photons. Infrared heat is photons. Ultraviolet radiation is photons. X-rays are photons. Gamma rays from nuclear explosions are photons. All of them are the same fundamental particle, just carrying different amounts of energy. Photons are the carriers of electromagnetism, the force that controls how charged particles interact. Every time an electron repels another electron, they are exchanging photons. Every time a chemical bond forms between atoms, photons are involved. Every living thing on Earth runs on chemistry, and all chemistry is driven by electrons exchanging photons. Here is the feature of photons that sets them apart from almost everything else in the Standard Model. They have no mass. Zero. And that zero is not an approximation. Experiments have tested the mass of the photon to extraordinary precision and found nothing. It is exactly zero. Because photons have no mass, they can move at the maximum speed the universe allows, what we call the speed of light. In empty space, a photon travels about 186,000 miles per second. That speed is so fundamental to reality that it is built into the fabric of space and time itself. Nothing with mass can ever reach that speed. As you push a massive object faster, it gets effectively heavier and harder to accelerate. Getting to the speed of light would require infinite energy. Only massless particles like photons can actually travel at that limit. The double nature of the photon is one of the most unsettling things in physics. A photon behaves like a wave and like a particle at the same time. Shine a beam of light through two narrow slits, and the light creates a wave pattern on a screen beyond, exactly as if water waves were passing through. But point a sensitive detector at the same screen, and the light arrives as individual clicks, individual particles, one by one. Both descriptions are real, neither one alone is complete. That duality is not a flaw in our understanding. It is how reality actually works at this scale. Now here is the strange twist. The photon has no mass, and yet it carries energy. It can knock electrons out of metal with a precise hit, an effect Einstein explained in 1905, and that eventually won him the Nobel Prize. The energy of a photon depends only on its frequency, how fast it oscillates. High frequency means high energy. That is why gamma rays from a nuclear reaction can damage cells, while the low-frequency radio waves passing through you constantly do nothing. The photon is simple in structure, complex in behavior, and central to every interaction involving charged particles. It connects light to chemistry to the forces holding atoms together. But the photon has a limitation. It only carries the electromagnetic force. The other forces need their own carriers. And those carriers have a very different story, one involving mass they should not have, a mystery that sat unsolved for decades. And one of the most famous predictions in the history of science, the Standard Model did not arrive fully formed. Nobody sat down, thought carefully, and wrote it out. It was built slowly, painfully across decades, by hundreds of scientists who sometimes hated each other's ideas, made wrong turns, fought over credit, and occasionally stumbled onto something brilliant by accident. The story starts in the early 20th century. Physicists had just discovered the electron. They were figuring out quantum mechanics, the rules that govern particles at tiny scales. Relativity was reshaping how they thought about space and time. It was a period of controlled chaos. By the 1930s, scientists understood atoms reasonably well. But as accelerators got more powerful through the 40s and 50s, they started finding new particles nobody had predicted. Not just a few, hundreds. Particles with strange properties. Particles that appeared briefly and fell apart. Particles nobody knew what to do with. The situation became so overwhelming that the physicist Enrico Fermi, one of the giants of the era, reportedly told a student that if he could remember the names of all those particles, he would have been a botanist. It felt like physics was falling apart. Decades of progress seemed to be buried under an avalanche of confusing new data. Then came the 1960s. Two physicists, Murray Gell-Mann and George Zweig, working independently, proposed something radical. All those particles were not elementary. They were combinations of smaller things. Gell-Mann called them quarks. Most of the physics community was skeptical, deeply skeptical. Quarks had never been seen. They had strange fractional charges that made no obvious sense. But the math worked, and the patterns it revealed brought order to the chaos. At the same time, theorists were attacking the forces. Sheldon Glashow, Abdus Salam, and Steven Weinberg found that electromagnetism and the weak force were two faces of one underlying force. They called it the electroweak force. That unification was a massive conceptual leap, and it came with a specific prediction. 3 heavy particles, the W and Z bosons, must exist. They were found in 1983, exactly as predicted. For the strong force, a separate theory called quantum chromodynamics took shape in the early 1970s, giving gluons and color charge their mathematical structure. By the mid-1970s, the pieces were fitting together: the 12 matter particles, 3 forces, 4 carrier bosons, and a still missing piece that theorists had been predicting since 1964. The framework had a name by then: the Standard Model. It was an achievement built on arguments, wrong guesses corrected, and the kind of stubbornness that refuses to accept chaos as the final answer. The people who built it worked in an era without the internet, without modern computing, passing handwritten papers across oceans. And the theory they created predicted a particle that would take another 4 decades to find. That particle changed everything, and the machine built to find it is still running today. In the 1950s, particle physics had a problem, a serious, embarrassing, threatening problem. Every time scientists built a more powerful particle accelerator, they found more particles. The list grew and grew: pions, kaons, lambda particles, sigma particles, omega particles, each one real, each one confirmed, each one with its own mass and charge and behavior, and none of them fitting neatly into any theory. By the early 1960s, the list had hundreds of entries, hundreds of particles, each one claiming to be a fundamental piece of reality. That number alone was a red flag. Fundamental things are supposed to be simple. If you need hundreds of ingredients, something is wrong with your recipe. Physicists called it the particle zoo. The name was meant to be slightly insulting. A zoo is something you look at without understanding. You observe the animals, you list them, you describe them, but you do not know the deeper rules that make an animal what it is. That was where particle physics stood: observing, listing, confused. The deeper crisis was theoretical. In classical physics, when you find a new object, you can usually figure out where it fits. But quantum mechanics at high energies behaved in ways that broke the usual tools. The math of the era could not handle interactions where forces were too strong. The calculations gave infinite answers where they should have given real numbers. Physicists had techniques to deal with that problem. For electromagnetism, a process called renormalization. But for the strong force, the method seemed to collapse entirely. Some physicists started to wonder if the Standard Model approach was even the right path. Maybe quantum field theory itself was the wrong framework. Maybe particles were not the right way to think about matter at all. Then a few things shifted the picture. An experiment at Stanford in 1968 fired electrons at protons at very high speed. If the proton were a smooth, solid ball, the electrons would scatter gently. Instead, they scattered at wild angles, bouncing back hard. It was almost exactly like the experiment a century earlier when Ernest Rutherford fired particles at gold foil and discovered the nucleus. Hard scattering meant hitting something small and dense inside the proton. The proton was not solid. It had structure. It had smaller things inside. That result gave Murray Gell-Mann's quark model physical reality. The proton had 3 quarks inside it. The hundreds of particles in the zoo were combinations of quarks in different arrangements. Suddenly, the chaos had an explanation. The particle zoo was not a collection of fundamental things. It was a collection of composite things, built from a much smaller set of ingredients. The particle zoo dissolved into a periodic table, And just like the periodic table in chemistry, the deeper structure pointed towards something even more fundamental waiting to be understood. But organizing the particles was only half the battle. The forces between them still needed a proper mathematical description. And the solution to that problem, when it came, was so unexpected that the physicist who found it almost did not believe it himself. Murray Gell-Mann was 24 years old when he arrived at the Institute for Advanced Study in Princeton, and he was already making older physicists uncomfortable. He had opinions. He had confidence. He had a habit of knowing things before other people had figured them out, and he was not shy about it. He was also, by most accounts, one of the most brilliant physicists of the 20th century. In the late 1950s and early 1960s, while the particle zoo was metastasizing into an impossible list, Gell-Mann started noticing patterns. The particles did not seem random. They grouped together, 8 particles here, 10 particles there, with masses and charges that followed a mathematical structure. He organized them into a framework he called the Eightfold Way, borrowing the name from a Buddhist concept of enlightenment. The structure worked. It organized dozens of particles into clean geometric arrangements. And in 1962, during a conference, Gell-Mann pointed at one of those arrangements and noticed a gap. One particle was missing from a set of 10. If the pattern was real, the missing particle had to exist. He predicted its mass, its charge, and its other properties right there. 2 years later, the particle was found at Brookhaven National Laboratory, exactly where Gell-Mann said it would be, exactly with the properties he predicted. But the Eightfold Way was a description, not an explanation. It organized the particles. It did not say why they grouped that way. Gell-Mann went deeper. He proposed that the patterns existed because the particles were built from even smaller things. He called them quarks, taking the name from a line in James Joyce's Finnegan's Wake, 3 quarks for muster mark. Quarks had fractional electric charges, which was deeply strange. Every electric charge ever measured in a lab was a whole number multiple of the electron's charge. Quarks required thirds and 2/3. That alone made many physicists dismiss the idea. George Zweig, a young physicist at CERN, proposed almost the same idea at almost the same time, calling his particles ACEs. He struggled even more to get his work taken seriously. His paper was never formally published through normal channels. But the math worked. The Eightfold Way patterns fell out naturally from quarks combining in groups of 2 and 3. The hundreds of zoo particles reduced to combinations of just a handful of quarks. Confirmation came slowly but steadily. The Stanford experiment in 1968 showed hard scattering inside the proton. Analysis of that data over several years pointed unmistakably to point-like particles inside. By the early 1970s, the quark model had enough experimental support that resistance became difficult to maintain. Gell-Mann won the Nobel Prize in Physics in 1969. Zweig never shared in that recognition, which remains a controversial chapter in the history of science. The quark model transformed particle physics, but it raised a new question immediately. If quarks exist and are the real building blocks, why has no experiment ever found a single quark on its own? Why do they always appear locked inside larger particles? That question led to the theory of the strong force and to one of the strangest properties of nature yet discovered. Empty space is not empty. That is the sentence that changes everything. Between the particles, between the atoms and the vacuum of space where nothing seems to exist, there is a field, an invisible presence that stretches across the entire universe, from one edge to the other, with no gaps, no interruptions. It was there a tiny fraction of a second after the Big Bang. It has been there ever since. And without it, the universe you live in could not exist. This is the Higgs field, and it does something that no other field in the Standard Model does. It gives particles their mass. Here is how to picture it. Imagine a crowded room full of people standing shoulder to shoulder. and nobody walks in and moves easily through the crowd. No resistance, no interaction. Then a famous celebrity walks in. Immediately, people cluster round. Fans reach out. The celebrity slows down because the crowd clings to them. The more the crowd interacts with the celebrity, the harder it is for them to move. The Higgs field is the crowd. The particles of the Standard Model are the people walking through. The ones that interact strongly with the field, like the W and Z bosons and the quarks, get slowed down. That resistance to acceleration is what we call mass. The more a particle interacts with the Higgs field, the heavier it is. The photon does not interact with the Higgs field at all, so the photon has zero mass and moves at the speed of light. The top quark, the heaviest particle in the Standard Model, interacts very strongly with the Higgs field. It is about 340 times heavier than a proton. Now here is the critical part. This is not just a convenient metaphor that physicists invented to explain an awkward equation. The Higgs field is real. It exists throughout all of space, and when a particle moves through it, the interaction that creates mass is a physical process, not a description. The theory of the Higgs field was proposed in 1964 independently by several physicists. Peter Higgs was one of them. The key insight was that a field filling all of space and interacting with particles could solve a serious mathematical problem. The equations for the W and Z bosons worked beautifully, except for one issue. They only held together if those particles had no mass, but experiments showed the W and Z were extremely heavy. The Higgs field mechanism resolved that contradiction in an elegant way. The field predicted a particle. According to quantum field theory, every field has a corresponding particle. Ripples in the electromagnetic field are photons. Ripples in the Higgs field are Higgs bosons. If the field was real, the particle had to be real too. The Standard Model had a missing piece, and physicists knew roughly what it would look like when they found it. They just did not know it would take nearly 5 decades of searching and the largest machine ever built by human hands to finally find it. For almost 50 years, one particle sat at the center of particle physics like a ghost, predicted by the math, required by the theory, confirmed by nothing. Every time a physicist calculated the Standard Model without the Higgs boson, the equations broke down. Predictions gave nonsensical answers, probabilities that exceeded 100%, infinities where there should have been real numbers. The Higgs field was the mathematical patch that made the whole structure work. But a patch you cannot see or measure is not a proven fact. It is a guess, no matter how elegant. So the hunt began. Finding a new particle requires energy, enormous amounts of it. The relationship between energy and mass, from Einstein's famous equation, means that to create a heavy particle in a lab, you need to supply enough energy to account for its mass, plus the energy needed to produce it in the first place. Smash 2 beams of particles together fast enough, and that collision energy can briefly become matter, including new particles that did not exist a millisecond before. The problem was, nobody knew exactly how heavy the Higgs boson would be. The Standard Model could say what the Higgs field did. It could not say precisely what mass the Higgs particle itself carried. Physicists had to search a range, and that range was wide. Accelerators through the 1980s and 90s set lower limits. Experiments at CERN's older machines ruled out certain masses. A machine in Chicago called the Tevatron searched and found nothing. Each null result was valuable because it narrowed the range. But the Higgs kept hiding. Then came the Large Hadron Collider, built inside a circular tunnel 27 miles around beneath the border of France and Switzerland. It took more than 2 decades to design and build, cost around $10 billion, and required contributions from thousands of scientists across more than 100 countries. 2 beams of protons traveling in opposite directions were accelerated to within a fraction of a percent of the speed of light, then steered to collide head-on inside massive detectors. The energy of those collisions exceeded anything humanity had ever produced in a lab. On July 4, 2012, scientists at CERN gathered in a packed auditorium and in overflow rooms and on video feeds worldwide. 2 separate experiments, teams of thousands of physicists who had worked for years analyzing billions upon billions of collision events, each announced the same thing: a new particle, consistent with the predicted properties of the Higgs boson, observed at both detectors independently. Some physicists in the room cried. Peter Higgs, who was 83 years old at the time, sat in the audience. He had proposed the particle in 1964. He had waited 48 years to see it confirmed. He won the Nobel Prize the following year, but the discovery of the Higgs boson was not the end of the story. It was the beginning of a new set of questions the Standard Model still cannot answer. Finding the Higgs boson answered one question and opened about 10 more. Physicists had their particle. They had confirmed the field was real. Now they had to understand exactly what it was doing and what it refused to explain. Start with what it does well. The Higgs field sits at a specific energy state, like a ball that has rolled down a hill and settled at the bottom. Physicists call this a broken symmetry, and it happens because the field's lowest energy state is 1, where the field is active, not 0. That active field interacts with particles passing through space, and those interactions produce mass. The amount of mass each particle gets depends entirely on how strongly it couples to the Higgs field. Scientists call this the coupling constant. For the electron, the coupling is small, so the electron is light. For the top quark, the coupling is enormous, around 173 times larger than the proton's mass. For the photon, there is no coupling at all, which is why light has no mass. Now here is the part the Higgs cannot explain. Why does the top quark couple so strongly to the Higgs field? Why does the electron couple so weakly? The Standard Model does not say. It treats those coupling values the same way it treats the 19 free parameters from earlier. It measures them from experiment and uses them. It provides no reason why they are what they are. That means the Higgs field explains how particles get mass. It does not explain the pattern of masses we observe. The spectrum of particle masses, ranging from the nearly massless neutrino to the enormous top quark, remains one of the deepest unsolved problems in physics. Then there is something called the hierarchy problem. The Higgs boson has a mass that seems far too small. In the mathematics of quantum field theory, masses of particles receive contributions from virtual interactions with every other particle in the theory. Those contributions should be astronomically large, pushing the Higgs mass to enormous values, unless something precisely cancels them out. Somehow, the Higgs mass stays relatively small. Either there is an extraordinary coincidence happening, or there is a deeper mechanism that nobody has found yet. The hierarchy problem has motivated decades of theoretical work. Supersymmetry, a framework that doubles the number of fundamental particles, was partly designed to solve it. Extra dimensions of space have been proposed as another solution. None of them have found experimental confirmation yet, and the Higgs has another limitation. It explains mass for particles that interact with the electroweak force, quarks, electrons, W and Z bosons, but the neutrino masses, which experiments have confirmed are small but non-zero, do not fit cleanly into the original Standard Model framework. To explain them, physicists have to add extra ingredients, and those ingredients are not yet settled. The Higgs boson is the most recently discovered piece of the Standard Model, and its discovery made clear that the Standard Model, as complete as it looks, is missing something. Possibly many things, but the deepest problem in the theory has nothing to do with particles or fields. It has to do with a force that shapes the cosmos on the largest scales imaginable, a force the Standard Model has never touched. Inside the Standard Model, buried in the mathematics, are 19 numbers, constants, fixed values that the theory uses to make its calculations work. Particle masses, force strengths, interaction rates without these numbers plugged in, the theory cannot make a single prediction about the real world. Here is the problem. The theory cannot explain them. Every single one of those 19 numbers has to be measured from experiments and then fed into the equations by hand. The standard model will tell you what happens after you give it those numbers. It will not tell you why the numbers are what they are. Think about what that means. The mass of the electron is roughly 9 times 10 to the power of negative 31 kilograms. If you ask the standard model why the electron has that mass and not twice that mass, or half, the theory has no answer. Measure it, plug it in, move on. For a theory that predicts the behavior of everything visible in the universe, that silence is deafening. Some of these numbers appear to be fine-tuned in ways that feel extraordinary. The strength of the strong force is set at a value that allows carbon to form inside stars. Shift it a few percent in either direction, and carbon production collapses. No carbon means no carbon-based life. Similarly, the mass of the electron relative to the proton is set at a ratio that allows atoms to be stable. Change that ratio significantly, and chemistry as we know it becomes impossible. These near-perfect values could be coincidences. They could be the result of deeper principles nobody has found yet. Or they could be explained by a framework so large that almost any value is realized somewhere, and life simply exists where the numbers happen to allow it. Physicists call that last idea the anthropic principle, and it is deeply controversial because it may be untestable. The strongest experimental fact here is straightforward. The standard model requires exactly 19 such numbers. A truly fundamental theory should ideally require 0. It should derive the constants of nature from deeper principles, the way you can derive the area of a circle from pi and a radius. The standard model cannot do that. It borrows from experiment and works from there. This is not a small critique. It points to something genuinely missing, a deeper layer of physics that would explain why the electron has the mass it does, why the strong force has the strength it does, and why the universe produced exactly the particles and forces it did, rather than something different. Some of the most creative theoretical work in physics over the last 50 years has been aimed at this problem. String theory proposes that particles are actually tiny vibrating loops of energy, and different vibrations produce different masses and charges. Grand unified theories try to merge the 3 standard model forces into one at extreme energies, which might constrain the free parameters. None of these ideas has produced an experimentally confirmed prediction yet. The 19 numbers sit in the theory like questions in bold letters. The universe chose them. The standard model uses them, and nobody knows why. That mystery alone would make the standard model incomplete. But there are bigger problems waiting. Problems that are not about what the theory gets slightly wrong. Problems about what it misses entirely. For all its mysteries and gaps, one fact about the standard model stands above everything else. When it makes a prediction inside its own territory, it is almost never wrong. And the predictions it makes are not vague, they are razor-sharp numbers. The most famous example involves the electron. The electron behaves like a tiny magnet. The strength of that magnetic behavior, called the electron's magnetic moment, can be calculated using the standard model to extraordinary precision. The prediction and the measured value agree to about 1 part in a billion. That is equivalent to measuring the distance across the continental United States, about 3,000 miles, and being accurate to within less than the width of a pencil. No other theory in science has achieved that level of precision, not even close. But that example is not unique. The standard model predicted the existence and the precise properties of the W and Z bosons before they were ever detected. When accelerators at CERN finally produced them in 1983, their masses and decay patterns matched the predictions exactly. The theory had been sitting there for over a decade, waiting for machines powerful enough to confirm what the math already knew. The same story played out with quarks, with gluons, with the details of how particles scatter at high energies. Every test that experimenters threw at the standard model over decades of increasingly powerful accelerators returned results that matched. This durability matters more than it might seem. A theory that only works for a few experiments could be lucky. A theory that keeps passing every single test across 50 years, across dozens of countries, in hundreds of different experiments, is telling you something real about nature. Every confirmed prediction is the universe agreeing with the equations. There is also something called global fits, where physicists take all the precision measurements from all the experiments ever run and check whether the standard model can simultaneously satisfy every single one of them. It does. The consistency is extraordinary. That track record is why physicists do not simply throw the standard model away when they point out its gaps. Discarding a theory that keeps working at this level of accuracy would be scientifically irresponsible. The goal instead is to extend it, to find the deeper framework that contains the standard model as a special case, while also answering the questions it cannot touch. This is the same logic that kept Newton's laws of motion in use after Einstein showed they were incomplete. Newton's laws work perfectly for slow speeds and everyday scales. Einstein's relativity was more fundamental and more general, but aerospace engineers still use Newton's laws to calculate spacecraft trajectories because they work within their domain. The standard model is the same kind of thing, brilliant within its range, reaching its limits at the edges, and the edges are coming up fast. The first and most dramatic edge is the one force the standard model never even tried to include, the force that sculpts galaxies, pins you to the Earth, and has resisted every attempt to be woven into the quantum framework. Gravity is next, and the gap it represents is not a technical fracture in our understanding of the universe. Gravity is the first force you ever felt. Before you could walk, gravity was already pinning you to the floor. Before you knew the word physics, gravity was shaping every arc and fall and orbit around you. It is the most obvious force in the universe, and the standard model has absolutely nothing to say about it. Not because physicists forgot, not because it seemed unimportant, but because every attempt to fit gravity into the same mathematical structure as the other three forces has failed. The math breaks down. The calculations produce infinities instead of answers. Two of the most successful theories in the history of science simply refuse to merge. Those two theories are general relativity, Albert Einstein's description of gravity, and quantum field theory, the framework behind the standard model. General relativity describes gravity as the curvature of space and time. Mass curves the space around it, and that curvature is what we experience as gravity. A planet orbits the sun because the sun's mass curves space-time in a way that guides the planet along a curved path. This is not just a visual metaphor. The math of general relativity has been tested to extraordinary precision. GPS satellites have to account for relativistic corrections, or their positions drift by miles per day. General relativity makes those corrections, and they are exactly right. Quantum field theory describes the other three forces as exchanges of particles, the gauge bosons, photons for electromagnetism, gluons for the strong force, W and Z bosons for the weak force. The theory works at the tiniest scales humans can probe. To combine these two frameworks, physicists would need a quantum theory of gravity, a description of gravity in terms of particles and quantum fields. The hypothetical particle that would carry gravity is called the graviton. It has never been detected. Here is why the combination is so hard. General relativity treats space and time as smooth, curved surfaces. Quantum field theory assumes a fixed, flat background of space and time over which particles move. The two pictures are fundamentally incompatible at their foundations. When physicists try to apply quantum techniques to curved spacetime, the calculations explode into nonsense infinities that cannot be removed the way similar infinities are removed in the standard model. The scale where this conflict becomes unavoidable is called the Planck scale. At energies and distances so extreme that even the Large Hadron Collider cannot approach them, both theories would need to apply at the same time. At that scale, the smooth curved spacetime of general relativity and the quantum uncertainty of particle physics crash into each other, and neither survives in its current form. This is the biggest known gap in fundamental physics. Modern science runs on two master theories. One governs the very large, one governs the very small. Neither description works in the domain of the other. And the universe does not actually split into large and small. It is one universe. A single theory should describe it. String theory is the most mathematically developed attempt to build that single theory. Loop quantum gravity is another. Both have generated enormous amounts of mathematics. Neither has produced a confirmed experimental prediction. The gravity problem is almost certain to require a revolution in physics, something on the scale of what quantum mechanics was in the early 20th century, a completely new way of thinking. And the universe has already shown physicists that something large is hiding, something that makes up more than a quarter of everything that exists. It has never been directly detected, and the Standard Model has no particle that could be it. Two theories walk into the same universe. Both of them are correct. They have been tested more thoroughly than almost any other ideas in science, and they cannot both be right at the same time in the same place. That is the central crisis in fundamental physics. General Relativity was published by Albert Einstein in 1915. It replaced Newton's picture of gravity as a force pulling objects toward each other across empty space. Instead, Einstein said space and time are a single fabric called space-time, and massive objects curve that fabric. The Moon orbits Earth because Earth's mass curves space-time around it, and the Moon follows the curve. Light bends around the Sun for the same reason. Time runs slower near heavy objects. Every one of these predictions has been tested and confirmed. Quantum mechanics emerged in the 1920s and 1930s from the work of Werner Heisenberg, Erwin Schrödinger, Niels Bohr, and many others. It described the behavior of particles at tiny scales and showed that nature at that level is fundamentally probabilistic. A particle does not have a definite position until it is measured. It exists as a spread of possibilities, and certain pairs of properties, like position and velocity, cannot both be known precisely at the same time. Both theories are spectacularly successful within their own territory. General relativity rules at large scales. It describes the behavior of stars, galaxies, black holes, and the expansion of the universe. The equations that govern black hole dynamics come from general relativity. The Big Bang model of the universe's origin uses general relativity. Quantum mechanics, extended into quantum field theory, and eventually the Standard Model, rules at small scales, chemical reactions, radioactive decay, and the interactions of subatomic particles. Every semiconductor in every computer and phone on Earth works because quantum mechanics is true. The problem appears at the extremes. Inside a black hole, gravity is so extreme that quantum effects cannot be ignored. At the very center, called the singularity, general relativity predicts that density becomes infinite and its own equations break down. Quantum mechanics should take over at some point in that extreme environment, but the Standard Model has no way to handle gravity. The first split second after the Big Bang is the same problem in reverse. The entire observable universe was compressed into a region smaller than an atom. At that scale, quantum mechanics dominates. But that region also had enormous mass and density, which means gravity was extreme. Both theories needed to apply simultaneously. Neither one can. For most of the history of modern physics, scientists could ignore this conflict because the scales where it mattered were so extreme that no experiment could probe them. General relativity handled the large. Quantum mechanics handled the small. The two domains rarely overlapped in practice, but the conflict is real, and any truly complete theory of nature has to resolve it. Several approaches have been tried. String theory proposes that particles are tiny vibrating loops of energy in a space with extra dimensions. The vibrations produce the different particles and forces we observe, including gravity. Loop quantum gravity takes a different approach, suggesting that space itself is made of discrete chunks rather than a smooth continuum, which allows quantum mechanics to apply at the smallest scales of geometry. Both have been under development for decades. Both have produced rich mathematics and genuine insight. Neither has made a prediction that experiments have confirmed. Somewhere between the domain of general relativity and the domain of quantum mechanics lies the deepest truth about reality. That truth is still hidden, and the Standard Model, for all its precision, sits entirely on one side of the divide, unable to cross. What sits on the other side is not just gravity. It is 95% of the universe itself. Something is holding the universe together. Something you cannot see, cannot touch, and cannot detect with any instrument that measures light. It does not emit light. It does not absorb light. Every telescope ever built, pointed at every corner of the sky, has returned zero direct signal from it. And yet it outweighs all visible matter in the universe by 5 to 1. The story of dark matter begins with a Swiss astronomer named Fritz Zwicky in 1933. Zwicky was studying a cluster of galaxies called the Coma Cluster, a collection of hundreds of galaxies bound together by gravity. He measured how fast the galaxies were moving within the cluster. Then he calculated how much mass the cluster would need to hold those galaxies in their orbits. The visible mass was nowhere near enough. The galaxies were moving far too fast. By Zwicky's calculation, the cluster needed roughly 400 times more mass than what was visible to explain the motion. He proposed that invisible matter was making up the difference. Most of the physics community ignored him. Decades later, an American astronomer named Vera Rubin made the same discovery at the level of individual galaxies. She measured how fast stars orbit around the center of spiral galaxies. In a normal galaxy, stars far from the center should move slowly, the same way Pluto moves more slowly around the Sun than Mercury does, because the gravitational pull weakens with distance. Instead, Rubin found that stars at the outer edges of galaxies move just as fast as stars near the center. The rotation curves were flat when they should have dropped off sharply. The only explanation that worked was invisible mass. Mass distributed not just at the center of the galaxy, but spread out in a large halo surrounding the entire visible disk. A halo of something that has gravity, but produces no light. Dark matter. The evidence has only grown since Rubin's work. Gravitational lensing, where the mass of a galaxy cluster bends light from objects behind it, allows astronomers to map the total mass of a cluster. The results consistently show far more mass than stars and gas can account for. The cosmic microwave background, the faint glow of radiation left over from the Big Bang, encodes patterns that match a universe containing roughly 27% dark matter. Computer simulations of how the universe evolved from the Big Bang to today only produce the large-scale structure we observe, the vast cosmic web of galaxy filaments and voids, when dark matter is included. Take dark matter out of the simulation, and the universe looks nothing like what we see. The Standard Model contains no particle that fits. Dark matter must interact gravitationally, because that is how we detect its presence. It must be electrically neutral, because it emits no light. It must be stable, because it has persisted throughout the entire age of the universe. And it must have been produced in the early universe in the right quantity. No known Standard Model particle checks all those boxes. Dark matter is real. It shapes every galaxy in the universe. And the theory that describes every particle ever detected in a laboratory has absolutely nothing to say about what dark matter is. That gap alone tells physicists the Standard Model is not the final answer. But the universe has another invisible secret, one even larger and even stranger. You have never seen a galaxy the way it actually is. Every image of a spiral galaxy, those beautiful pinwheels of light with glowing cores and sweeping arms, shows only the visible part. The stars, the gas clouds, the dust, the glowing remnants of dead stars. All of that, everything captured in every photograph, is roughly 1/6 of the total mass of a typical galaxy. The other 5/6 surrounds it, invisible, in a vast spherical halo that extends far beyond the visible disk. Dark matter does not live where the stars are, it wraps around them. That halo is what makes galaxies stable. Without it, a spiral galaxy like our own Milky Way would fly apart. The stars in the outer arms are moving too fast for the visible mass at the center to hold them. The gravitational pull from all the visible stars, gas, and dust combined is not strong enough. The dark matter halo supplies the additional gravity that keeps everything in orbit. Think of it this way. The luminous galaxy you see in photographs is like a small log floating in a massive invisible ocean. The log is real. The ocean is real, but you can only see the log. The effects of dark matter extend beyond individual galaxies. On larger scales, dark matter is the skeleton of the entire universe. After the Big Bang, matter was spread nearly uniformly through space, with tiny ripples of slightly higher density in some regions. Dark matter, which does not interact with light or normal matter in the same chaotic way, could begin clumping under gravity much earlier than ordinary matter could. Those dark matter clumps formed first. Then ordinary gas fell into the gravitational wells the dark matter created. Stars formed inside those wells. Galaxies grew around them. Without dark matter forming that early scaffolding, the large-scale structure of the universe would never have assembled fast enough. The timeline does not work. Galaxies as we see them today, billions of years after the Big Bang, should not exist without dark matter seeding the process. Gravitational lensing makes this visible in a striking way. When astronomers look at distant galaxy clusters, they see arcs of light around the clusters. These are images of even more distant galaxies behind the cluster's gravity. By measuring how much bending occurs, astronomers can calculate the total mass responsible for the lensing. The result always exceeds the visible mass by a large factor. The invisible mass, mapped this way, matches the distribution expected for dark matter halos. One of the most dramatic examples came from an event called the Bullet Cluster. Two galaxy clusters collided. The hot gas from each cluster, which interacts electromagnetically, slowed down and piled up between the two clusters. But the dark matter halos, which barely interact with anything, passed straight through each other and kept moving. Astronomers could map the hot gas using X-rays and map the total mass using lensing. The mass was separated from the gas. That separation was the clearest direct evidence that dark matter is genuinely a distinct substance, not a modification of gravity. It passed through a collision that stopped ordinary matter cold, and none of it appears in the Standard Model. The next question is not just whether dark matter exists. It does. The question is what it is. And the answer to that question may require particles that no current theory has confirmed. Dark matter has rules. The universe set them, and any candidate particle has to pass all of them. So far, no particle in the Standard Model comes close. Rule 1. Dark matter must be electrically neutral. Anything with electric charge interacts with photons, meaning it produces or scatters light. Dark matter is invisible to every electromagnetic telescope ever built, so it carries no electric charge. Rule 2. Dark matter must be stable across cosmic timescales. The universe is about 13.8 billion years old. Dark matter has been present since the very early universe and is still here now. Any particle that decays quickly cannot be dark matter. Rule 3. Dark matter must interact gravitationally. Every piece of evidence for dark matter comes from its gravitational effects. It bends light. It holds galaxies together. It shaped the large-scale structure of the universe, so dark matter must have mass and must respond to gravity. Rule 4. Dark matter must have been produced in the right amount in the early universe to match what we observe today, that roughly 27% of the total energy content. Now run those requirements against every particle in the Standard Model. The quarks carry color charge and form composite particles, not neutral enough, not stable in isolation. The charged leptons, meaning the electron and its heavier cousins, carry electric charge. Ruled out immediately. The W and Z bosons are heavy and decay in a fraction of a second. Ruled out. The Higgs boson decays almost instantly. Ruled out. Gluons carry color charge and are confined inside protons. Ruled out. That leaves neutrinos. Neutrinos are electrically neutral. They barely interact with anything. They are stable. They have a tiny but non-zero mass. For a while, physicists hoped neutrinos were the answer, but calculations killed that hope. Neutrinos are almost massless and move at speeds close to the speed of light. In the early universe, they would have been racing around too fast to clump under gravity. Dark matter needs to clump to build the structures we see. Fast-moving particles smooth things out instead of bunching up. Neutrinos cannot be the dark matter responsible for galaxy formation, so the Standard Model is empty of candidates. This has driven theoretical physicists to propose entirely new particles that exist beyond the Standard Model. The most studied candidates are called weakly interacting massive particles, often shortened to WIMPs. These hypothetical particles would be heavy, electrically neutral, stable, and would interact only through gravity and possibly the weak force. That profile makes them nearly invisible to ordinary detectors, but detectable in principle through rare collisions with atomic nuclei. Decades of experiments have searched for WIMPs, large underground detectors filled with liquid xenon or other materials wait for the rare moment a dark matter particle would scatter off a nucleus. Nothing confirmed has been found. Other candidates exist. An extremely light particle called the axion was originally proposed for a completely unrelated problem in the Standard Model, but also fits some dark matter requirements. Searches for axions are ongoing. The score so far is clear. Every dark matter search has found nothing confirmed. Every Standard Model particle has been ruled out. Something real is shaping the universe. And while this search continues, something even more mysterious is pushing the universe apart at an accelerating rate. The universe is expanding. That much has been known since the 1920s, when astronomer Edwin Hubble showed that distant galaxies are moving away from us, and the farther away they are, the faster they recede. The natural assumption was that gravity would eventually slow that expansion down, maybe stop it, maybe pull everything back together. In 1998, two independent teams of astronomers were trying to measure exactly how much the expansion was slowing. They used a specific type of exploding star, called a Type I supernova, as a distance marker. These explosions have a consistent brightness, so by measuring how bright they appear from Earth, you can calculate how far away they are. Then you compare their distance to their speed, and you can trace the history of expansion. What they found stopped the physics community cold. The expansion was not slowing down, it was speeding up. Galaxies were not decelerating under gravity, they were accelerating away from each other. Something was pushing the universe apart, and that push was growing stronger over time. Both teams checked their data repeatedly. They looked for errors. They found none. The result was confirmed by independent observations within years. In 2011, the leaders of both teams shared the Nobel Prize in Physics for the discovery. Something invisible was driving the acceleration. Physicists named it dark energy. The name is honest about how little is understood. It is called dark because it cannot be seen. It is called energy because it behaves like a form of energy inherent to space itself. Current measurements place the amount of dark energy in the universe at about 68% of its total energy content. That makes it the dominant component of the cosmos. Everything you can see, every star, every galaxy, all ordinary matter is about 5%. Dark matter is about 27%. Dark energy is the remaining 68%. The Standard Model has nothing to say about dark energy. The equations of particle physics do not naturally produce a term that drives cosmic acceleration. Physicists have tried to calculate what the vacuum energy of quantum fields should contribute to something like dark energy. The answer they get is a number about 120 orders of magnitude too large. That is a 1 followed by 120 zeros times bigger than the observed value. That gap between prediction and observation is the largest known discrepancy in all of science. The most common way to parameterize dark energy in cosmological models is through a term in Einstein's equations called the cosmological constant, which Einstein himself originally introduced and later called a mistake. The universe turned out to need it after all, just not for the reason he thought. What the cosmological constant physically represents is unresolved. Whether dark energy is a fixed property of space, whether it changes over time, whether it is connected to some new field or particle, remains unknown. New telescopes and surveys are measuring the acceleration with increasing precision, searching for any variation that might hint at the underlying mechanism. Dark energy is real. It controls the ultimate fate of the universe, and it lives entirely outside anything the Standard Model describes. The universe is mostly made of things physics cannot yet explain. Science rarely surprises itself as completely as it did in 1998. Two teams of astronomers had spent years measuring distant supernovae. Their goal was quantitative and specific. They wanted to measure the deceleration parameter, a number that describes how fast the expansion of the universe was slowing down due to gravity. The debate was about whether the universe would expand forever or eventually collapse. Almost everyone assumed it was one of those two futures. Almost everyone assumed the expansion was slowing. The key tool was a Type A supernova. These stellar explosions happen when a dense remnant of a dead star, called a white dwarf, pulls in matter from a companion star until it crosses a critical mass threshold and detonates. Because the detonation always happens at nearly the same mass, the explosion always releases nearly the same amount of energy. Astronomers call this a standard candle, a light source with known brightness that you can use to calculate distance, the way knowing the wattage of a light bulb lets you estimate how far away it is based on how bright it appears. The Supernova Cosmology Project, led by Saul Perlmutter, and the High Z Supernova Search Team, led by Brian Schmidt and Adam Rees, were running competing measurements. They were finding supernovae at distances of billions of light years, far enough back in time to sample different eras of the universe's history. The supernovae were fainter than expected. Fainter means farther away. Farther away than the models predicted meant that the universe at that point in cosmic history was expanding faster than the models said it should be. The team sat with that result for months before publishing. The implication was too strange to announce without certainty. If the supernovae were fainter than expected, either the standard candles were not standard after all, or the universe's expansion was not slowing. It was accelerating. Every systematic error was hunted for and eliminated. Dust that might dim the light. Variations in the supernovae themselves. None of them explained the signal. Both teams, working independently with different data and different instruments, reached the same conclusion. The expansion of the universe is accelerating. Something is pushing space itself outward at an increasing rate. The discovery redrew the map of cosmology overnight. The calm, predictable story of a universe coasting under its own gravity was replaced with a dynamic, accelerating cosmos, driven by something completely unknown. For the Standard Model, the discovery was another wall. The theory describes particles and their interactions inside space. It says nothing about what drives the large-scale behavior of space itself. The cosmological constant, the simplest mathematical way to capture the acceleration, fits into Einstein's equations of general relativity. It does not emerge from quantum field theory in any natural way. The universe handed physicists an enormous new fact. The acceleration is real, measured, confirmed. The explanation is still missing. And the missing explanation may be connected to something even stranger than a force pushing space apart. It may connect to why the universe contains anything at all. Pause for a moment and think about everything you have ever seen. Every person, every building, every mountain and ocean and star, every galaxy photographed by every telescope ever pointed at the sky, every particle ever detected in every accelerator ever built. All of that is 5% of the universe. The remaining 95% is dark matter and dark energy, two things the Standard Model cannot describe. The most successful theory in physics, the one that predicts electron behavior to 1 part in a billion, is a complete description of 5% of reality. That fraction needs context to feel as strange as it is. Imagine you are handed a jigsaw puzzle. You assemble it carefully and produce a perfect, complete-looking picture. Then someone tells you that the box contained 2,000 pieces total, and you only used 100 of them. The picture you made looks coherent. It makes sense internally, but you are missing 1,900 pieces, and you have no idea what they look like. That is the situation of the Standard Model. The 5% that the Standard Model describes is called baryonic matter, named after baryons, the class of particles that includes protons and neutrons. Baryonic matter is what atoms are made of. It is what stars, gas clouds, planets, and living things are made of. It glows, absorbs light, and participates in chemistry. It is the only matter we have ever directly detected, but the universe is not organized around baryonic matter. It is organized around dark matter, the vast cosmic web of galaxy clusters and filaments that stretches across the observable universe. A structure sometimes called the cosmic web is the skeleton of dark matter scaffolding. Ordinary matter fell into that skeleton and lit up. What you see in the night sky is the luminous face of an invisible framework. Dark energy adds another layer. It does not just make up 68% of the universe's energy content. It controls the future. As the universe expands under dark energy's influence, the density of ordinary matter and dark matter decreases. Galaxies spread apart. Eventually, clusters of galaxies will accelerate away from each other faster than light can cross the growing distance between them. Galaxies outside our local group will vanish from our observable universe entirely. The Standard Model has nothing to say about any of this long-term cosmic fate. It describes the particles inside atoms, the story of where those atoms go, what surrounds them, and what drives the universe they inhabit is mostly outside its scope. Physicists are aware of the irony. The theory they have tested most thoroughly covers the smallest slice of reality. The bulk of the universe remains theoretically dark. What makes this even more pressing is that the 5% itself should not exist. According to the Standard Model's understanding of the early universe, the matter that built stars and planets should have been annihilated completely in the first seconds after the Big Bang. The fact that you exist is, from one perspective, a violation of what the Standard Model predicts. For every particle of matter, nature produces a mirror twin, same mass, same behavior, opposite charge. These mirror twins are called antimatter. An anti-electron, called a positron, has the same mass as an electron, but carries positive charge instead of negative. An antiproton has the same mass as a proton, but opposite charge. Every quark has an antiquark. Every lepton has an antilepton. When matter and antimatter meet, they annihilate. Both particles vanish in a burst of pure energy. No wreckage, no debris, just light. The Standard Model and the physics before it suggest that the Big Bang should have produced matter and antimatter in equal amounts. When the universe was born, it was a place of extreme energy, and that energy converted into particle-antiparticle pairs symmetrically. One particle, one antiparticle, again and again, across the entire young universe. If the balance had been perfect, the story ends quickly. Every matter particle would have found its antimatter partner. Everything would have annihilated. The universe would have been left with nothing but a vast sea of light, photons carrying the energy of all that annihilation expanding into empty space. No stars, no planets, no atoms, nothing, but something went wrong with perfect symmetry. Or rather, something went right. Somewhere in the first fraction of a second after the Big Bang, the balance tipped. For every billion antiparticles produced, roughly 1,000,000,001 particles of matter were produced. The billion pairs annihilated. The extra one survived. That leftover 1 in a billion is everything you see. Every star, every galaxy, every atom in your body is the residue of an almost perfect annihilation that happened 13.8 billion years ago. The question that haunts physics is why that tiny imbalance existed. For an asymmetry between matter and antimatter to occur, 3 conditions have to be met simultaneously. These conditions were identified by the physicist Andrei Sakharov in 1967. The universe must violate the perfect symmetry between matter and antimatter. The universe must favor certain processes that create more matter than antimatter, and those processes must happen in conditions where the universe is not in perfect thermal balance. The Standard Model contains all 3 of these ingredients. In principle, it can produce an asymmetry. The weak force does treat matter and antimatter slightly differently, a property called charge parity violation. Physicists have measured this difference in experiments. But when they calculate how much asymmetry the Standard Model actually produces, it falls short, far short. The imbalance the Standard Model generates is far too small to account for the matter-dominated universe we live in. Something else tipped the balance. Something outside the Standard Model. Some process or particle or force that the current theory does not contain. The fact that you exist, that the Earth exists, that any matter at all survived the early universe, is evidence that the Standard Model is incomplete. The universe itself is the experiment that proves it. The numbers that describe the antimatter problem are almost impossible to hold in your head. In the first moments after the Big Bang, the universe was dense and hot beyond any comparison. Particle-antiparticle pairs were constantly being created from the violent energy of that environment. Quarks and antiquarks, electrons and positrons, created in enormous numbers, annihilating almost immediately, then created again. The universe was a constant storm of creation and destruction. As the universe expanded and cooled, pair production slowed, annihilation caught up. The slate was nearly wiped clean. From that near-perfect cancellation, a residue survived. Current measurements suggest that for roughly every billion antimatter particles in the early universe, there were about 1,000,000,001 matter particles. That excess of 1 per billion is what built the visible cosmos. Physicists express this imbalance as a ratio. The number of baryons, meaning protons and neutrons in the matter made from them, compared to the number of photons in the universe today. The ratio is about 1 baryon for every 10 billion photons. That is the fingerprint of the original asymmetry, frozen into the cosmos after the annihilation was complete. The Standard Model, despite containing charge parity violation in the weak force, generates an asymmetry many orders of magnitude smaller than that ratio. Many orders of magnitude means not slightly too small. The Standard Model's contribution is so inadequate that it cannot explain even a tiny fraction of the observed matter excess. Something else happened. Some process in the early universe created significantly more matter than antimatter, and the Standard Model did not cause it. Physicists have proposed mechanisms. One idea, called leptogenesis, suggests that heavy particles beyond the Standard Model decayed asymmetrically in the early universe, producing more leptons than antileptons. That lepton asymmetry then converted into a baryon asymmetry through a process the Standard Model does actually contain, called Sphaleron transitions, which were active at the extreme temperatures of the early universe. Another approach proposes new sources of charge parity violation beyond what the Standard Model contains. Different versions of supersymmetry, or models with extra Higgs fields, could enhance the asymmetry to the required level. None of these mechanisms has been experimentally confirmed. They are viable proposals constrained by what experiments allow, but not yet proven. What is confirmed is the shortfall. The Standard Model's contribution to the matter-antimatter asymmetry is insufficient by an enormous margin. The universe we observe could not have formed from Standard Model physics alone. You are made of matter. The fact that you are made of matter and that antimatter does not surround you and annihilate you is evidence of physics that remains undiscovered. The most mundane fact about your existence points to something missing from the best theory ever written, and the missing piece does not stop at matter and antimatter. There are particles inside the Standard Model that have already cracked the theory open. Particles so light that their mass should be exactly zero, but whose behavior in experiments showed otherwise. The gap between what the Standard Model predicts and what the universe shows is not a small rounding error. It is a fundamental failure at one of the deepest questions physics can ask. Why does anything exist? To make this concrete, consider what charge parity violation actually means in the Standard Model. The weak force treats matter and antimatter slightly differently in certain decay processes. This is real and experimentally confirmed. Particle accelerators have measured the difference in how certain mesons, which are particles made of a quark and an antiquark, decay compared to their antimatter counterparts. Those measurements are precise. The asymmetry is real, and it is far too small. Physicists have calculated the total baryon asymmetry that can be generated by Standard Model charge parity violation during the phase transitions of the early universe. The result is a number roughly 10 billion times smaller than what the universe actually shows. The observed baryon-to-photon ratio needs an asymmetry that the Standard Model simply cannot produce. Beyond the size of the asymmetry, there is a second problem. The Standard Model's electroweak phase transition, the process during which the Higgs field switched on in the early universe, was not energetic enough to sustain the generation of asymmetry efficiently. For leptogenesis and baryogenesis mechanisms to work properly, the phase transition needs to be what physicists call strongly first order, meaning it should have proceeded through distinct bubbles of the new phase, forming and expanding, allowing asymmetries to accumulate at the bubble walls. Standard Model calculations show the transition was too smooth and gradual for this to be efficient. Two separate failures. The asymmetry is too small, the mechanism is too weak. Both point in the same direction. New physics beyond the Standard Model was active in the early universe. This is not just a theoretical problem. It drives real experimental programs. Physicists study the properties of the Higgs boson at the Large Hadron Collider, partly to look for deviations from Standard Model predictions that might hint at an extended Higgs sector capable of driving a stronger phase transition. Experiments called B-factory accelerators study the decays of particles containing bottom quarks in extreme detail, hunting for new sources of charge parity violation. So far, no confirmed new source has emerged. The experiments are constraining the possibilities, ruling out large classes of proposed new physics. But the answer has not appeared. This is the situation. The universe contains matter. The Standard Model cannot explain why. The experiments hunting for the explanation have not found it. The gap sits open. And below that gap, in the deep structure of the Standard Model itself, are particles that already broke one of its predictions by having mass when they should have had none. For a long time, supersymmetry looked like the answer to almost everything. It was a beautiful idea. The Standard Model contains two types of particles: matter particles, called fermions, which have a property called half-integer spin, and force carrier particles, called bosons, which have integer spin. These two families behave very differently under the rules of quantum mechanics. Supersymmetry proposed a deep symmetry connecting them. Every fermion would have a boson partner. If supersymmetry were true, the number of fundamental particles would double overnight. The electron would have a partner called the selectron, the quark would have a squark, the photon would have a photino, the Higgs boson would have multiple superpartners, These new particles had never been seen, but their absence was explained neatly. At the energies accessible to older accelerators, the superpartners would be too heavy to produce. They existed, the theory said, just out of reach. Supersymmetry was appealing because it solved multiple problems simultaneously. It addressed the hierarchy problem, the question of why the Higgs boson mass stays small despite quantum corrections that should push it enormous. In supersymmetric theories, the corrections from standard model particles and their superpartners cancel each other out. The Higgs mass stays naturally small. Supersymmetry also provided a dark matter candidate. The lightest superpartner, which would be stable because it had no lighter particles to decay into, would be electrically neutral and would interact only weakly. That profile matched the requirements for dark matter almost perfectly. The particle even had a name, the neutralino, and supersymmetry hinted at unification. The three forces of the standard model, electromagnetic, weak, and strong, have different strengths at ordinary energies. When physicists extrapolate those strengths to higher energies, they come close to meeting at a single point. In the standard model, they miss. In supersymmetric extensions, they converge precisely. That convergence suggested a grand unified theory, one force at extremely high energies splitting into three at the energies we observe. The Large Hadron Collider was, in part, designed to find supersymmetry. When it turned on, physicists expected superpartners to appear. The Higgs mass measurement and earlier experiments had set ranges for where the lightest superpartners should be. The machine ran. Billions of collisions happened. The analysis came back. Nothing. No superpartners have been found at the Large Hadron Collider. The masses originally expected have been ruled out. The parameter space where simple supersymmetric models could hide has been heavily constrained. The lightest neutralino as a dark matter candidate has been pushed into a corner by both collider results and underground dark matter searches. Supersymmetry is not dead. Versions with heavier superpartners still exist within the allowed experimental bounds. Some physicists continue working on it, but the natural, elegant supersymmetry that solved the hierarchy problem and predicted accessible superpartners has not appeared where experiments looked for it. The most promising extension of the standard model is under pressure, and the theory that was supposed to come after it may require something even more radical than doubling the number of particles. String theory starts with a single change to the picture. Instead of treating particles as points, treat them as tiny loops. Strings, vibrating loops of energy so small that no instrument can see their structure. Strings that would make a proton look enormous by comparison. Different vibration patterns of the same string produce different particles. One vibration is an electron, another is a quark, another is a photon. The entire particle content of the standard model and more emerges from the same underlying object vibrating in different ways. It is as if the entire orchestra of the universe is playing one instrument. That shift from point particles to strings resolves the central conflict between general relativity and quantum mechanics. When you try to apply quantum mechanics to gravity using point particles, the calculations explode into infinities. The mathematics breaks. But strings have a finite size, tiny beyond imagination, and that size smooths out the most violent quantum fluctuations at the smallest scales. The infinities tame themselves. Gravity and quantum mechanics can coexist in the same framework. String theory naturally produces a force carrier for gravity, a massless spin-2 particle called the graviton, without being forced to add it by hand. In this sense, string theory does not just include gravity. It requires gravity. The theory cannot be written without it. That feature made string theory extremely exciting when it emerged as a serious research program in the 1980s. Physicists had spent decades failing to merge gravity with quantum mechanics. String theory merged them automatically. The cost was extra dimensions of space. The mathematics of string theory is only consistent in 10 dimensions. The universe we experience has 3 dimensions of space and 1 of time. String theory requires 6 more spatial dimensions. Those extra dimensions are proposed to be curled up into shapes so tiny, smaller than anything that can be probed experimentally, that they are invisible to every measurement. The shape of those extra dimensions determines which particles exist and what properties they have. Different shapes, called compactifications, produce different physics, and the number of possible shapes is enormous, perhaps 10 to the power of 500. That is a landscape of possible universes so vast that it may be unnavigable. That landscape problem is one of the central criticisms of string theory. A theory that can produce almost any physics is a theory that predicts almost nothing specific. Physicists argue vigorously about whether the string landscape is a feature representing the many possible universes in a multiverse, or a failure of the theory to make testable claims. String theory has not produced a single confirmed experimental prediction. After 4 decades of development, it remains the most mathematically rich framework in physics that has yet to make contact with measurement. Its defenders argue that the mathematics is too deep and the relevant energy scales too far beyond current experiments for confirmation to be possible yet. Its critics argue that a theory untested after 40 years is approaching philosophy more than physics. The debate continues. The theory survives, and the machine most capable of resolving these questions has already run for years without finding what the theories expected. 27 miles of tunnel, buried about 300 feet underground, curving in a circle beneath the border of France and Switzerland, 2 beams of protons traveling in opposite directions at speeds that bring them within a fraction of a percent of the speed of light. Magnets cooled to temperatures colder than outer space to steer the beams. Detectors the size of apartment buildings, assembled from tens of millions of individual components, watching the collisions. The Large Hadron Collider is the largest and most complex scientific instrument ever built. It cost about $10 billion. Thousands of physicists from over 100 countries contributed to building it and analyzing its data. It was built with a clear purpose: find the Higgs boson, search for new physics beyond the Standard Model, look for evidence of supersymmetry, extra dimensions, dark matter candidates, or anything else that experiments had not yet been powerful enough to see. The Higgs boson was found in 2012. That was the triumph. The celebration was real, the Nobel Prize was awarded, and the Standard Model was confirmed in its last major missing piece. Then the machine kept running. More collisions, higher energies, more data. Scientists analyzed billions of events looking for anything that did not match the Standard Model predictions. The Standard Model kept winning. Every distribution of particles emerging from collisions matched the theory. Every decay rate, every cross-section, every angular pattern. The precision of the measurements improved year after year, and the Standard Model continued to describe the results within experimental uncertainty. This is simultaneously the greatest validation of the Standard Model and one of the most frustrating outcomes in modern physics. Every physicist hoped for something unexpected: a particle that appeared in the wrong number, a distribution that peaked somewhere new, a signal that said something unknown was contributing to the collisions. Nothing confirmed emerged. The Large Hadron Collider has run 2 major operating periods and is now in its 3rd. Energy and luminosity have both increased. The dataset is vastly larger than the early run that found the Higgs, and still the Standard Model holds. This does not mean new physics does not exist. It means new physics if it involves particles that couple to protons and can be produced in collisions at current energies, is not in the accessible range. The new physics might involve particles too heavy for even this machine to create. It might involve interactions too rare to stand out above background noise with current data volumes. It might involve particles that decay in ways that are difficult to detect. There are also tantalizing hints, small deviations from Standard Model predictions that appear in some measurements and then fade with more data. Anomalies that generate excitement and papers and debates, then resolve as statistical fluctuations. Physicists call them look elsewhere effects. The more places you search, the more likely you are to find a false positive by chance. The next generation of colliders is already being discussed. Machines larger than the Large Hadron Collider, with higher energies, are in planning phases. Whether they will find something new is unknown. What is known is that the Standard Model cannot be the end. The universe has already shown that. And buried in the data from decades of neutrino experiments is a confirmed crack in the Standard Model that physicists have known about for 25 years. The original Standard Model made a clean prediction about neutrinos. They have no mass. Zero. Exactly zero. The theory was built that way on purpose, because having massless neutrinos simplified the mathematics and matched every experiment available at the time. That prediction is wrong. Neutrinos have mass. It is tiny, far smaller than the mass of the electron. But it is not zero. And the proof came not from a particle accelerator, but from the sky. The sun produces enormous numbers of electron neutrinos through the nuclear reactions in its core. These neutrinos travel outward at nearly the speed of light, pass through the entire body of the sun without difficulty, and stream across the 93 million miles to Earth. Some fraction pass through Earth's detectors. In the 1960s, a physicist named Raymond Davis Jr. built a detector deep inside a mine in South Dakota. He filled a tank with 100,000 gallons of dry cleaning fluid and waited for neutrinos from the sun to interact with it. He could count the interactions and estimate the neutrino flux. He found about 1/3 of the neutrinos the solar models predicted. For years, the discrepancy was debated. Either the solar models were wrong, or something was happening to the neutrinos on their way. The answer came decades later. Neutrinos do not stay as one type. An electron neutrino produced in the sun can transform into a muon neutrino or a tau neutrino as it travels. Then it can transform back. The three types oscillate, shifting identity over distance. This process is called neutrino oscillation. Neutrino oscillation cannot happen if neutrinos have zero mass. It requires the different neutrino types to have slightly different masses. The observation of neutrino oscillation is direct proof that neutrinos have mass. The Nobel Prize in Physics for 2015 went to Takaaki Kajita and Arthur MacDonald, the leaders of two experiments that confirmed neutrino oscillation, one in Japan and one in Canada. For the Standard Model, this was not a small anomaly. It was a confirmed failure. The original theory explicitly predicted massless neutrinos. Nature disagreed. The model needed to be patched. Physicists added mechanisms to give neutrinos mass, the most popular involving extremely heavy particles that have never been observed. But the patch is an addition from outside the original framework. The neutrino mass problem also connects back to the matter-antimatter asymmetry. The leading mechanism for generating the observed asymmetry, called leptogenesis, requires heavy neutrino-like particles that decay in an asymmetric way. The fact that neutrinos have mass and oscillate is consistent with this picture, though the heavy particles involved remain undiscovered. Neutrino physics is one of the most active areas of experimental particle physics today. Future experiments aim to measure the exact masses of the three neutrino types, determine whether neutrinos and antineutrinos behave differently, and search for a specific type of decay that would confirm whether neutrinos are their own antiparticles. The neutrino is the most abundant matter particle in the universe, after photons. It passes through everything. It refuses to interact, and it has already told us, quietly and without drama, that the Standard Model, as originally written, was wrong. Physicists use the phrase, theory of everything. It sounds like an overstatement. It is not. The goal is precise. A genuine theory of everything would be a single mathematical framework that describes every particle, every force, every interaction in the universe, from the inside of a proton to the structure of space-time itself, without putting anything in by hand and without leaving anything out. That theory does not yet exist. but physicists have a clear list of what it would have to accomplish. First, it would have to contain the Standard Model as a special case. Every confirmed prediction the Standard Model makes, the electron magnetic moment, the Higgs boson mass, the decay rates of particles, would need to follow from the deeper theory at the appropriate energies. A theory that contradicted the Standard Model in its tested domain would be wrong. The new framework has to reproduce the old results and go further. Second, it would have to include gravity. A unified theory must describe all four forces. That means merging general relativity with quantum mechanics in a way that produces finite, sensible answers at every energy scale, including the extreme conditions near singularities and during the Big Bang. Third, it would have to explain dark matter. The identity of the dark matter particle, or whatever dark matter turns out to be, would need to emerge naturally from the theory, not be inserted to match observations. Fourth, it would have to address dark energy. Whether dark energy is a fixed property of space or something dynamic, the theory would need to produce the right value, not a number 120 orders of magnitude too large, the right number. Fifth, it would have to explain the matter-antimatter asymmetry. The theory would need to contain enough charge parity violation, implemented through the right mechanism, to generate a baryon-to-photon ratio matching what the universe shows. Sixth, it would have to explain the 19 free parameters, the masses of the particles, the strengths of the forces, the mixing angles in the quark and lepton families. All of these would need to be derived from deeper principles rather than measured and plugged in. Seventh, it would have to be testable, a framework that can accommodate any experimental result without making specific predictions is not a scientific theory. The new physics would need to make predictions at energies reachable by future experiments, or make predictions about cosmological observations that can be confirmed or ruled out. That is a long list, and every item on it corresponds to a confirmed gap in the Standard Model. Each one is a question the current theory cannot answer. Some physicists believe all these requirements will eventually be satisfied by a single elegant framework, perhaps a version of string theory, or something not yet conceived. Others argue that the questions might require several distinct theoretical advances rather than one grand unification. What everyone agrees on is that the Standard Model is not the last word. The evidence for that is everywhere, in the dark matter halos of galaxies, in the acceleration of the universe, in the mass of the neutrino, in the matter surrounding you that should not have survived the Big Bang. The next layer of physics is real. It is hiding, and the experiments chasing it are getting more powerful every year. A theory can be incomplete and still be the most useful tool in history. Those two things are not contradictions. The Standard Model is not wrong about what it describes. Inside its tested domain, it is extraordinarily right. The precision of its predictions is unmatched by any other theory in science. When physicists calculate something within the framework of the Standard Model and then measure it in an experiment, the agreement is, with rare exception, remarkable. The comparison to Newton's laws is the most useful one. Isaac Newton wrote down the laws of motion and gravity in the late 1600s. Those laws worked spectacularly for 2 centuries. They predicted the motions of planets. They were used to calculate the orbit of Neptune before Neptune was discovered, by predicting where an unknown planet had to be based on gravitational disturbances to Uranus. Then Albert Einstein showed that Newton's laws were not the deepest description of gravity. General relativity contained Newton's laws as a special case, valid at slow speeds and weak gravity, but different and more accurate in extreme conditions. Relativistic corrections matter for GPS satellites, for Mercury's orbit, for the behavior of black holes. And yet, aerospace engineers still use Newton's laws every day to calculate rocket trajectories and satellite orbits. At the speeds and masses involved, the correction from general relativity is tiny. Newtonian mechanics is accurate enough to be useful, and it is far simpler to work with. Knowing a theory is incomplete does not make it useless. The Standard Model works the same way. Chemists do not need to think about quarks when they study how molecules bond. Biologists do not solve quantum chromodynamics equations to understand cell division. Even particle physicists, when calculating processes at energies well below the scale where new physics is expected, use the Standard Model as their working tool. It gives them the right answers. The Standard Model will remain in use even after the theory that supersedes it is found, just as Newton's laws remain in use today. The successor theory will contain the Standard Model as a special case. In the energy regimes where the Standard Model has been tested, both theories will give the same answers. The new theory will give additional answers, correct answers, in the regimes where the Standard Model is silent. That is how science actually works. Knowledge accumulates. Frameworks get extended. Incomplete theories are not discarded when better ones arrive. They are absorbed, their domain of validity clarified, their results explained as limiting cases of something deeper. The Standard Model is the most precisely tested theory in the history of science. Its incompleteness is not an embarrassment. It is a map of where to look next. Every gap in the theory, every question it cannot answer, points toward undiscovered physics. The gravity problem points toward quantum gravity. Dark matter points toward new particles. The matter-antimatter asymmetry points toward new sources of charge parity violation. Neutrino masses point toward heavy particles beyond current reach. The broken theory is also a treasure map, and the people following that map have the most powerful tools in history at their disposal. Every era of physics has had a moment where the field looked almost complete. In the late 1800s, some physicists thought the major work was done. The laws of thermodynamics were solid. Mechanics worked. A few small puzzles remained, but the main picture seemed clear. Then, quantum mechanics arrived. Then, relativity. The few small puzzles turned out to be the loose threads that, when pulled, unraveled the entire previous picture and revealed something far stranger and more profound. Physics is in a similar position today. The Standard Model is the most powerful framework ever assembled. Its predictions pass every test within its domain. And yet the loose threads are visible. Dark matter, dark energy, gravity, the matter-antimatter asymmetry, neutrino masses, the 19 unexplained constants. Each one is a question the theory cannot answer. Something is coming. The only unknown is when and in what form. The search is real and active. The Large Hadron Collider continues running, accumulating more data, with its detectors upgraded between runs. Experiments deep underground in mines around the world watch for the rare collision of a dark matter particle with an atomic nucleus, with each new generation of detector more sensitive than the last. Telescopes map the large-scale structure of the universe with increasing precision, tracing the distribution of dark matter and measuring the properties of dark energy. Neutrino detectors buried under mountains or sunk into polar ice record the faint interactions of the most elusive particles in the Standard Model. New facilities are being planned. A proposed electron-positron collider would study the Higgs boson in far greater detail than the Large Hadron Collider can, probing the properties of the Higgs field for any deviation from Standard Model predictions. A much larger Hadron Collider, several times the circumference of the existing one, is under discussion in Europe and China. These machines would probe energies where some theories predict new particles must appear. Theoretical physicists are not waiting. New frameworks are being explored. Some revisit supersymmetry in forms that evaded previous searches. Others explore dark matter candidates beyond the original WIMP picture. Some work on models with extended Higgs sectors that could explain the matter-antimatter asymmetry. A smaller community pursues approaches to quantum gravity that do not rely on string theory. The answer could arrive through a single dramatic discovery, a new particle appearing in a detector, a dark matter particle scattering off a nucleus at an underground lab. a precise measurement of the Higgs boson's couplings that deviates from the Standard Model prediction by just enough to point toward new physics, or it could come from an unexpected direction entirely. The history of physics is full of breakthroughs that came from angles nobody was looking at. Quantum mechanics grew from the problem of blackbody radiation. Relativity grew from the problem of electromagnetism and moving reference frames. The next revolution could grow from an anomaly that currently seems minor. What makes this moment remarkable is not the gaps, it is the precision with which those gaps are known. Physicists understand exactly where the Standard Model fails and exactly how well it succeeds. That precision is itself a form of knowledge, a map of the territory that still needs to be explored. The Standard Model is the most successful theory in physics. It is also, without question, unfinished. Both of those things are true, and the distance between what it explains and what it cannot is where the next chapter of physics will be written. The frontier is open, the questions are real, and the universe is still hiding most of itself.